So thank you everyone for coming to my talk. This follows on from Fred's stuff about what's new at DCF. I'll be presenting on a summer project I did at DCF, predominantly on radiation chemistry modelling. There we go. on radiation chemistry modelling, which links into this MIRaCLE that's being developed at DCF to support users. So the main idea of this project was what happens when ions interact with water. The ionizing radiation will excite and ionize the water, which causes this cascade of chemical reactions. It's a very, very non-linear process, so we require simulations to kind of probe these processes that are happening here. There are multiple ways to simulate these kind of chemical reactions. The most common method is a Monte Carlo simulation, which says, give me a set of particles and I will tell you how they evolve over time. This is particularly good for very high energies and very short time scales, but at low energies, long time scales, where the number of particles increases tens of thousands, hundreds of thousands, due to this cascading effect from the chemical reactions, it quickly becomes unmanageable using a Monte Carlo simulation. At DCF, the DCF team have been working on this product called MIRaCLE, which seeks to, instead of using a particle description of the underlying process, it uses concentrations instead. So we can represent the simulations using functions rather than individual particles. MIRaCLE attacks the reaction-diffusion equation directly, which is this master equation of chemical kinetics that governs the process of the water radiolysis that we're talking about. It splits the reaction-diffusion equation into some different steps, a diffusion step and a reaction step, and in doing so, it alternates between two different descriptions of the concentration. One is a spatial-based description and one is a frequency-based description using a fast Fourier transform. This allows the computation to be really quite efficient. So I'll just go over a brief example now that was done last year in the nuclear industry. So one of the key factors about MIRaCLE that I'm getting to is that it's incredibly fast. In this setup here, the MIRaCLE team looked at water radiolysis on thin layers of water on plutonium storage. But the main thing getting to this is that they were able to perform hundreds of simulations over, I think, is it 15 orders of magnitude there? Yeah, 15 orders of magnitude, all on a laptop in a single day. So there's this great exploration of the parameter space that's allowed by MIRaCLE here. Moving on to my project a little bit more now. So we're really interested in this water radiolysis from ions and ion beams. So we'll look at a single ion passing through water. This is something that relates back again to this what's new at DCF. This is the simulation that we want to do could quite easily be performed experimentally on the end of line 3 at DCF. Additionally, it also relates to this new equipment that's being built and put on the end of the beam line, where we can investigate thin liquids, thin layers of water on samples. One thing about this as well, so the simulation that I'm attempting to develop here is a single ion going through water, and because of the symmetries of the beam line, we can reduce down the complexity of this problem down to one dimension by just simulating across the radius here. So we take the single ion, we pass it through water, we can get the number of reactive species produced from this paper here, MIRaCLE, and then if we know the amount of energy transferred to the water, we know our initial conditions, this set of reactive species. Our initial conditions are given by the sums of normal distributions, which take into account the kinetics that happen in the physical stage of the interaction of the ion with the water. The results of this simulation give us a lovely equilibrium here and a predictable ratio, which could be used to compare with the experiment. We ran a few simulations here that span 6 orders of magnitude in time. Here it's given for a 1 MeV proton and a 75 keV alpha particle, but realistically we can simulate over a very large range of LETs. One really important thing here is that the simulation time is only seconds long using MIRaCLE, so it allows for this really easy rolling of redevelopment of simulations. Equally, these simulations also provide a wonderful baseline comparison for interfacial effects of water. So looking back at I briefly mentioned about irradiating thin films of water, both on the end of the beamline. Since these simulations are in bulk water, we can then infer the interfacial effects from the comparison. However, I think one of the most interesting results here that we've got is that we observe a hollowing out of the concentration distributions for aqueous electrons and hydrogen radicals at different times during the reaction. Here I've got polar plots at 500 nanoseconds, so the colour is obviously corresponding to the concentration of the ions, and we're looking down the beamline here. I've also got radial plots along here, tracing out just one dimension along the edge, and then so the height on the y-axis here corresponds to this concentration, the colour on the radial plots. You can see with these animations of the electron, the solvated electron concentration over time, there's this hollow effect here that's being pushed out. These aren't just observed in MIRaCLE either. So looking back at simulating these in Monte Carlo, for example, Balder has simulated these in using a Monte Carlo simulation, and there's a hollowing out effect here as well. But the key thing is, in the Monte Carlo simulation, it takes many days to simulate and to recreate. So from this, we found some really interesting phenomena produced by these inhomogeneous simulations. But the main point is that MIRaCLE has provided me with this wonderful, easy to work with framework to develop simulations that could support experimentalist DCF users in their work at DCF. But MIRaCLE can't just be, or isn't just applicable to water. It's a general solver of the reaction-diffusion equation for chemical kinetics. So there's applications in atmospheric science, planetary atmospheres, and a lot more as well. And that concludes my talk.